Half of machine learning is linear algebra, and the other half is probability. Models don't output certainties, they output odds, and the way we score those odds, the loss behind nearly every classifier, comes from a deep idea about information itself. Today, probability, surprise, and cross entropy. A classifier doesn't say this is a cat, it says 70% cat, 20% dog, 10% fox. Its output is a probability distribution, a set of beliefs over the possible answers. To train it, we need a way to measure how good that distribution is compared to the truth. That measurement is the whole episode. First, the basics. A probability distribution assigns a number to each possible outcome. Two rules: every number is between 0 and 1, and they all add up to exactly 1. That's it. A confident model piles most of its probability on one outcome. An unsure model spreads it out. The shape of that distribution tells you how certain the model is. Now suppose the true answer was cat, and the model gave cat 70%. That 70% is the likelihood, how probable the real data was according to the model. High likelihood means the model expected what actually happened. Low likelihood means reality surprised it. Good models assign high probability to things that turn out to be true. And that gives us a training principle: maximum likelihood. Choose the model's parameters to make the observed data as probable as possible. Nudge the weights so the things that really happened get higher and higher probability. Almost every model you've met is underneath doing exactly this, maximizing the likelihood of its training data. But we usually phrase it the other way around. Here's the bridge, the idea of surprise. If something the model thought was certain happens, that's no surprise at all. If something it thought was impossible happens, that's a huge surprise. Mathematically, surprise is the negative logarithm of the probability. Likely event, tiny surprise. Rare event, enormous surprise. Information is just surprise measured. Look at the curve of negative log p. When the probability is near 1, surprise is almost 0. You basically knew it would happen. As probability falls toward 0, surprise climbs without limit. This is the same steep wall we saw with the loss back in episode 3. And that's not a coincidence. It's where the loss comes from. Take the average surprise across a whole distribution and you get its entropy. A sharp, confident distribution has low entropy, so few surprises. A flat, uncertain one has high entropy, lots. Entropy measures how unpredictable a source is. A coin that always lands heads has 0 entropy. A fair coin has the most. It's the amount of genuine uncertainty. Now the star of the show. Cross entropy measures the average surprise when you use the model's predicted distribution to describe events that actually follow the true one. If the model's beliefs match reality, that surprise is minimal. The more the model's distribution is wrong, the higher the cross entropy climbs. It's a distance between what the model believes and what's true. And for classification, this collapses to something simple: the exact loss from episode 3. Since the truth puts all its probability on one correct class, cross entropy reduces to just the negative log of the probability the model gave that correct class. Confident and right, tiny loss. Confident and wrong, massive loss. The famous classification loss is just cross entropy in disguise. Closely related is KL divergence, the extra surprise you pay for using the wrong distribution instead of the true one. It's 0 only when the two distributions are identical and grows as they drift apart. Cross entropy equals the true entropy plus this KL gap. So minimizing cross entropy is really minimizing that gap, pulling the model's beliefs toward reality. And here's the elegant punchline: 3 things you'd think were separate are secretly the same. Minimizing cross entropy, maximizing the likelihood of the data, matching the true distribution. There are 3 views of one act: making the model's probabilities agree with the world. That single principle drives the training of almost every modern model, including the ones writing and drawing today. So, that's the probabilistic half of machine learning. Models output distributions. We score them by surprise, and the loss that does it, cross entropy, is just maximum likelihood wearing the clothes of information theory. Next time, we close out the math toolkit with the idea that governs whether a model will actually generalize. The bias variance trade off. See you there.